So salam alaikum. So good morning all. Welcome back to our today's session. Today we will continue where we stopped yesterday. We are still in our chapter, the mechanics of learning. I'm sharing my screen, cool? Right?
Yes.
Okay. So just to be recap before we move into the next session. Yesterday what we discussed is about the mechanic of learning, how learning works in deep learning. When we talk about deep learning, we look at we discuss about the step learning works, and we discuss about how we use the learning as taking it as parameter estimation. When we say parameter estimation, is like when we have an input and we have an output, we are trying to make prediction, but we try to estimate parameters to find best parameter that will make a perfect prediction that will actually reduce the errors. That is the learning. That is parameter estimation. We try to estimate best parameters. That is what we have seen yesterday, and we saw that yesterday that this is how deep learning works. You have an input, your data, you go through some layered function, you make a prediction, you have true value, and now you use LX function to find a score, the difference between it. And now with this loss score, if it is large, you update your weight using something called optimizers, and now you keep this going, this a loop until your loss score is very small, right? That's what we discussed. And now we discuss about a toy problem. So we all know deep learning. In deep learning, our function is not linear, but we said, okay, let's start giving an intuition how deep learning works with a small problem, toy problem. And we assume our function of deep learning will be a kind of linear. We use this data set, and we visualize our data. We assume the function to be linear. This is not true in some sense because we are just using our deep learning is complex functions, and we assume the function is somehow linear. With that, we said we want to optimize this stuff, right? We discussed about how we actually find the error. We find the error and we use something called activation function, which change the function from linear function because this is a linear, so it will not make any sense using linear. We need to change it to some non-linear function. We use some non-linear function on this, which we use what we call activation functions, which are basically one of the function or aim of activation function is to change this from linear form to some kind of complex form, because deep linear network cannot learn from linear transformation. They can learn because they have some kind of structure. So we need to change the linearity to somehow complex form, non-linear. So that's why we use activation function. And the next chapter will discuss a lot here about the activation functions. And now we say, okay, to find the difference, we use what we call mean absolute error or mean squared error. That's what we discuss. And we say, okay, now let's go to Pytorch or deep learning. We see how we can implement this process. So the first thing here we can see is to define the model that can do prediction from input to here. We've defined a model. So how can we do that? We said, okay, let's do that. We have our input here. We have the true value. So input here is this X, which is this guy. And now we define a model. So how we define the model? So this is a model. Given the model, given the weight and B, that is the bias, and given the input. So this is it. Given the input, given the weight, which are the weight and bias, given them, how can we transform from here? We go here. So we need to give weight, we need to give input. So this is the model we define, right? This is the model we define. So this is the model, given the input, given the weight, we return this expression. So this is the function that do everything. So this is the model. So we say, okay, now we do the we have the model that calculates from this guy to this guy to make a prediction. So what this guy returns, what this model returns is basically the prediction, because what is this guy times this guy plus B, this guy times this guy plus B, it gives us this, and this is a prediction, right? So the model return a prediction. So this means that we have a prediction from here to here. We have a prediction. Now what we need to do is to find the difference between the prediction and true target. That is using the loss, right? So we need to implement a loss. So this is what we did yesterday. Okay, let's implement the loss. How can we implement the loss? By finding the difference and the square and return it, right? So you can see that this is a loss. So now we saw that we find the loss, and this loss code that we have here, this is something that what it returns here is the loss code thing. So now we can see we have the model, we have the loss. Now what remains for us is to do this. If this loss is very large number, then we need to go back. We update the weight. We need to change this weight. But how can we change this weight? That is where the main problem is. How can you change this weight, right? If this is very large error, how can you change this weight? Maybe then these are 10, in the first instance is 10, and now you have a very large. How can you change this weight to an error, to weights that will actually change this code to minimal? So that is where that we have a lot of problem we need to implement. We use what we call some optimization problem. So if you look at it, we are trying to minimize this loss from given this weight. Then it is what we call minimization problem, right? Minimize, because we want to minimize the loss. So for us to solve the minimization problem, there are many algorithms. One of the widely used algorithm is called gradient descent. So for us to reduce that loss, we need to use gradient descent. So one of them, right? So what gradient descent is, from the name gradient, we are trying to find the derivative using gradient. So we need to use like some change in your value, some change in W, and some change in another parameter B, find the rate. This is as we stock. This is how we do it. Change the change of loss with respect to your weight. So we need to update those weight. For us to update the weight is to say or the previous weight minus something alpha, which is we call linear rate, times this gradient. This is how you update. This is called gradient descent, and there are a lot of it. And what I will advise is for us to go and try to find a lot about the gradient descent, because I've not discussed it a lot here. So yeah, so you see here, this is the implementation of the change of weight. We said W linear rate. What is linear rate? Linear rate is basically defined how fast we will move along the direction. So this is it. And now it means we need to write a formula that can do this. And that is, yeah, so there is something here that we call, you can see this, plot is what we call convex, because if you look at, we have what we call non-convex problem. So this is a convex. It means it has a single minimization, because we are doing problem of minimization, right? So if this is our problem, our plot, then we have a single minimum value here. So we'll try to, if this is the initial weight, what we do is to change this weight. Initially, we change it iteratively, change this weight until it comes to this. This is the global minimum. This is, but if you have non-convex problem, then you can have many issues. So this is the global minima. This is the local minima, the global. But you can have what is called local minima, and we can have what we call saddle point. So one of the problem of gradient descent, our function which are non-linear, is that they are not convex. They are somehow non-convex. So we will try to find how can we reach the global minima. So there is a lot to do that with the issue with that is one of the problem of gradient descent. But in essence, that is what we discussed yesterday, and now we implement this stuff using calculus, and this is it, like gradient, calculate the gradient like this, and yeah, this is also the gradient, and finally we put all this formula to here, gradient. So this, all those English, this is what is implemented, the gradient. We implement a gradient function, which is this, that calculate this guy, gradient, this one. So what we need to do is to say this, if we want to update a weight, we say weight is equals weight minus linear rate, this gradient function that we calculate. So let me show us in totality what we did. So this is finally, for us to train a deep learning neural network, it means we need the number of epoch, that is the iteration we want, because you can see we need to iterate and change the weight. And now we need what we call linear rate, which is how fast we go. And we need to give the parameters, that is bias and weight. And we need to give our true value and the initial value, right? So here we say, okay, let's go for epoch in this guy. That is the epoch, the number of epoch we want, for range in 1 to this, that is from the beginning to the last, right? These are the parameters, we set them, and now we do the model, that is the prediction, right? And after the prediction, what we do next is to find the loss, right? After finding the loss is what? We need to update the weights. How can we update the weight? For us to update the weight, we must find the gradient. This is how we find the gradient. This is what we, yeah, how can we need to find the gradient here with respect to this way to update this parameter. So this is what we do. And now how can we now update the parameters? So for us to update the parameters is using this, what we discuss here. This one, which is weight minus parameter, linear times this gradient. So this is the implementation here. Parameter is linear rate minus gradient. So this is it. Now, so this continues. So this is basically the implementation of how we do learning mechanics of learning, how it works briefly. But this is a manual way. The better way we will see is what we call using Pytorch that actually will abstract all this process. So let's look at it. So that is a brief what we did yesterday, and this is what we will do today. Now, this is the engine block of Pytorch is what we call AutoGrad, right? AutoGrad. What do we mean by auto? I mean AutoGrad. It automatically calculates the gradient automatically. Do back propagation, everything. You don't need to calculate the gradient. You don't need to bother about any mathematical mathy stuff. Everything is done automatically. So let's look at what we do. The issue we have, we just saw a simple example of backpropagation and writing the analytical expression for the derivative of berry y kaza da kaza. And that is not a fun, right? It's particularly not a quick. So that is not something easy. The solution is to use what we call Pytorch AutoGrad that do this automatically. So you don't need to bother about what we discussed last week and yesterday. You can even forget it, but just get the concept. What you need to know is what we do in this section, which is called using AutoGrad to do deep learning. Right. So Pytorch AutoGrad, its function is basically to do automatic differentiation. So let's look at what we can do. Now, solving the same problem we saw using AutoGrad, let's go and see it. So here I import my torch and import my NumPy, and here I initialize my values, right? The C centimeter and unknown value, right? Can you see them? I initialize them. But remember, because we know in deep learning, when we create a value, we must convert it to tensor, right? We cannot use we cannot use this as the way they are. We must convert them to tensor. We already know that. So that is why we do this. But remember, yesterday we talked about normalizing the input, right? So this T on non-function, we normalize it. We said, okay, how can we normalize it? By using some value, multiply everything. So now here we normalize this. We discussed this yesterday because without normalization, your problem will not converge faster, right? So you can normalize your input and your network will converge faster, right? So this is the model we discussed yesterday. That is given the input, given the weight, return the prediction. So this is prediction that will return. So we have the prediction here and we have the loss, right? Just as we saw, we have the loss. But remember, our gradient, our main problem in this is not the calculating the loss, it's not calculating the loss, the model. Or the main problem is how can we do back propagation, right? Automatically, we see this, we saw this analytically. It's a little bit cumbersome. So we want to see how we can use that with Pytorch. So let's again initialize our parameters. So let's initialize the parameters. So in Pytorch, if you want to do use AutoGrad, what you need to do is that all the parameters you're gonna use, you need to do what we call you set what we call required grad equals to 2. It means you want to actually create a graph for all these parameters. So let's look at what we mean. So in Pytorch, when you build what we call a graph. So when you have your input, this is X, and this is your weight, this is your bias, and now you try to do. So Python will try to build what we call a graph, right? Yeah, it's called graph, right? Yeah, graph. So it will try to build this graph and try to come back with it and do back propagation using this graph. It build this graph. So for us to say, okay, track graph for all these parameters, then we need to set, where is it? Okay, we need to set our parameters required grad equals to true, right? So it means these parameters we have, look at our two parameters we have, right? This one and this one, we say, okay, we have required grad equals to. This is the main important point with that. So now, since you can use this to actually set your parameter with required grad equals to true using this approach while you are creating your tensor, but you can also use another approach. Assume you create your tensor first, but you have not set this required grad equals to true, then you can use this method. You can call this param, this variable, right? From you can say grad required grad equals to true. You can set it in either this way or this way, right? So this is something new we don't know. So this is how you can actually set your gradient. So now how can we compute the gradient? Now, for us to compute the gradient, we need to call what we call backward. So here, when we have our input, we make prediction. This is our loss. Now this is a true target. This is a loss. We need to do back propagation on the loss. Back propagation on the what? Loss, to do this, to do back. So in Pytorch, what you need to do, it just, you said, call loss that backward. Gaba ɗaya wannan ya maka differentiation ɗinka, ba ruwanka, kawai call loss. Remember here, this is what we do in the previous, I think, okay, let me show us how we do in the previous one. So in this one here, where we do it analytically, look at how we calculate the loss. So look at how we do what we do. So we have our model, we have our loss, right? But for us to calculate the gradient, look at what we need to call one gradient function. We need to put some input. Can you see them? The weight, the bias, the input, the prediction, right? The prediction and the true and whatsoever. And this grad function, remember, this is how we create the function. This is the function, right? Inside this function, you can see some kind of gradient, derivative of the loss, of the prediction of the loss, and derivative of the weight, derivative. Can you see that? Which are based on these formulas, right? In Pytorch, you don't need to do that. Pytorch will do everything for you. So what you need to do is just call this. You can see if you create your loss. So here we have our model. Maybe I can say, okay. So if you look at this one here, I put this one. Okay, this is true. Okay, so let me, no. Okay, let me take this one. Yeah, and say my model, something like this. Can you see that if I have my model, I can say, okay, model here, model. So you can create your model, the first step, right? You can see how we create our model. That is the forward pass. Given the input, create a model to make prediction. It is model here that will make prediction, right? So now here we have a model. Call the model with given parameters. These are the parameters: weight, y, kada, and given the input, which is x. Can you see the input x? And this will return, the model will return the prediction. Can you see that? Now, how can we calculate the loss? Given the target with the prediction, right? Now, the prediction is, this is what you will return prediction. We have our prediction. Let me call this one my prediction, right? Maybe prediction. You have your prediction here. And you have your prediction here, and you have your true target, right? So you call the loss function. The loss function, what the loss function does, we already know. It basically, given the prediction, can you see that? And it calculates the difference, stuff like that, right? So now here you can see we calculate the loss. Now, what we have our loss. What do we need to do? We need to do back propagation to find the direction where we. Now, what you need to do is just call that loss, call it backward. This will do the back propagation, right? And now, how can you update your parameters since you do back propagation? Back propagation will show you how to do update your parameters. Now, let's look at how we update our parameters in the previous one. So here you can see when you find the gradient, what you need to do to update your parameters is say, okay, is parameter, the new parameter is the old parameter minus learning rate times gradient, right? You put your gradient times learning rate. Yeah, this is how we update our parameter. Remember, this is it. Can you see that? Old parameters minus learning rate times this, the new parameter. So this is it. So how can we do that with the Pytorch? This is how we said our parameters, that is the old parameter times grad. Wannan kawai zaka kirawo, it will do the behind the scene. All this calculation that we saw here, Pytorch will do everything. It will do this, learning rate times this, parameter at this, it will do that. So when we said params, the grad, this will, behind the scene is doing this calculation. Behind the scene is doing this calculation. Para all the parameter minus learning rate times grad, right? That is what we do here, right? So we can see here, that's, let me change it to the previous one, just, yeah. So that is what we have. So now here you can see this is our parameters that updated, right? So yeah, any question before we continue? Want to add something? Any question before we continue? Or want to add something? Please ask question or add anything you feel like want to add. Yes, Sayed, Tunde, Sada, Idris, Ibrahim, Falalu, Awal, Amina, Aliyu, Abubakar, Abdullah. Anything you want to add something before we move on? Remember, yesterday discussion was a bit better, another discussion, eh?
Yeah, but as you're comparing what we did yesterday and today, it's clear that these are the steps, and then this is how, instead of going through the longer step, this is the function that is actually is there on the Pytorch.
Yes,
Instead
yes.
of following that longer process, then this
Yes.
is the easy way to do it. So
Yes.
it's self-explanatory on its
Okay,
by
okay, cool. All right. Okay, anyone want to add something or say? Okay.
Doctor, I want to ask a question.
Yes.
The values 1 and 0, are these the default value for the weight and bias? Because from the formula autograd, I see this, yeah, here we have 1.0 and 0.0. And we say parameters require grad true. So I don't know if 1 and 0 are the default values for the weight and bias.
Yeah, so here what we mean is that we
Yes.
set our parameters. So parameters for Kodama, what you need to do is if you want to do, you need to set your parameters, right? For example, this is the weight and bias.
Bias, yes, yes.
You setting them so comma y. Let's assume you setting since y. Now, when you set them, you make prediction. You say, I have the loss. You have very large loss. What you need to do is to come back here to see what parameters idan loss ɗinka is large, back propagation shi zai gaya maka yadda za ka yi updating ɗin wannan weight ɗin. To sai ka canja su. To wannan abin da muka yi, we set the parameters farko, initialize them. Yeah, so we initialize them. Yeah, so yeah.
Thank you, Doctor.
Yeah, wow. Okay, so it makes sense if we are asking question and are trying to, yeah, if you want to add something on top of that. Yeah, so that is what we do. So at this point, the grad attribute parameter contains the derivative of the law with respect to each element. So let's look at something accumulating grad function. So there is a problem. What is the problem? Look at it. This is it. You have an input, you have your model, you make prediction, you compare with the two target and compute the loss, right? Now you call the backward here. Where is the backward? Okay. You call this backward and you tells you to update the weight, right? Now you said, okay, you have the weight. Now at this point, you have the weight, right? Now you say, okay, this is a new weight. I want to update. New weight, I update the weight, right? What do you call that? Let me, okay, okay. You have your the gradient here that you update the weight. Now you go for another round. So when I go for another round, I do prediction with the new weight and this, and I have a new loss score. Now I need to use gradient or back propagate to update, to find the gradient and update the weight. But remember, in the last step, I have a new gradient, right? When I update the gradient now, it will accumulate the gradient with the previous one. It will keep accumulating the gradient because previously you have one gradient in the first round. When you come back, you have another gradient. You keep accumulating. This will be a problem because the previous gradient, the first gradient is used to select this weight. The subsequent gradient, we don't want to use the previous gradient to select the next weight. We need to use a new gradient, fresh gradient. This means that we need to, when we create a loss, when we find the gradient and choose a weight, we need to destroy the gradient or set it to 0 and now go to another prediction. And now when we calculate another gradient, it will not accumulate on top of the previous one. So that is what we call the notion of accumulating gradient. One, in calling backward will lead derivative to accumulate at limit node. We need to zero gradient explicitly after using it for parameter update. So what this is saying is that when we use a loss score here, we find it, so we call it backward, this function backward. Can you see we call it a loss? It will calculate grade, this backward will calculate gradient, which is grad. Now, when we calculate this grad, it is using this grad that we know how can we update this way. The value of this grad that we know, it is what we know how we can, but if we are in the first round, this grad will be there. If we come for the next round, if we do not actually zero this grad, the next grad will build on top of this. So that we need to do what is called zero grad. That is accumulating gradient function. So we need to call this function if grad is not to none, that is the previous one. So 0, 8. So param the grad is the 0 will zero the previous. So let's look at how we can do that. So this is our training, new training, the previous one. That is Yeah, okay, the old one. Okay, so this is the old one we saw. You remember this is, we call the epoch line rate parameter, and now we saw it for this, we params, we do the model, we do the loss, we call the gradient right here, and now we update the parameters, right, using the gradient time line rate, this one. Now how can we do now with the Pytorch? So with Pytorch, number of epoch the same, our line rate the same, we give the parameters, we give this input. Now we said this is still the same. Now remember here, if params grade is not known, 0.8, meaning if this is not the first iteration. So for the first iteration, params, the gradient is set to true, right? For the first iteration, right? Because we set it to true for the first iteration, remember? We set it to true. But if it is not first iteration, that is the second, we don't want to accumulate. So always set it to 0.8 so that we don't accumulate. So this could be done at any point within the loop. So here we do the model, the prediction. Given this, here we calculate the loss, and now here we calculate the backward, right? Now, how can we update our parameters? For us to update the parameters, what we can do is here we said, okay, learner rate times params the grad. Here we'll come to it lately, but what this is doing here is that remember here, while we are updating the parameters, we need not our gradient, because these parameters, they are set to true, right? They have gradient equals to true. But while we are updating the parameters, we want to set the parameters, we want to reset them that gradient is false. So this function touch.noGrad set your parameters to without gradient, because doing calculation with gradient set to true, it will build what we call a graph. But we don't want that graph because it takes much more time, much stuff, right? So we want to set the gradient equals to false. So here we update the parameter, but with the gradient equals to false. So this is how the learning will work. What differs from this guy is this. Can you see at this step, we don't have this guy. Can you see that we don't have this guy? We call backward, right? And here you can see we don't have the notion of gradient is accumulator, right? So here we have something here that zero the gradient, but here also we said, okay, because our gradient is set to true, doing this updating parameters, we need parameters, previous parameters to update the new parameter, but the old parameters gradient is set to true. So what we need to do is we set the no gradient, so that this will do normal calculation without gradient. Normal calculation, multiplication and stuff, and do that. That is the function of this guy, right? So this is how Pytorch help us to do that. But let's see more about that. So let's see how it works. So training the loop. So we remember here we calculate what we call training loop, and this is the training loop, right? Training loop. So for us to train a deep learning network, we just need to call the training loop and put in the input parameter. So what our input parameter, you can see we have what we call epoch, we have learning rate, we have params, and we have this guy. So let's call this. So we can see training loop. We want to train a deep neural network. Number of epoch 5,000, learning rate is this, parameters. But remember parameters here, we said, okay, tensor, we give them as tensor, but we require, we said the parameters required grad equals to true, right? We set here the parameters, we set grad equals to true, and now we look at our input, we use the normalized data. Remember, we use the normalized data, right? So now having this guy, we can see that we can train the model here in this way. When we train the model here, you can see, we'll see so it gives us this result. We can see this is our optimized weights, right? Optimized parameter that we can use. So this is a optimized. Remember, when you say you are training deep learning, when you are training, you are always finding parameters, optimized parameter that you can use to train anything. So you can see this is the one. So if you look at the previous sessions, when we trained the network, let's look at our result, because we use everything. You can look at it, 5.36 minus 17, right? The parameter. Look at still the same. Can you see that? So the result is the same as we got. It means that while we are capable of computing derivative by hand, we no longer need to, right? So this means that the previous one we have been using, where we are calculating the gradient with hand, we don't need to do that. We can use what we call Pytorch AutoGrad. So AutoGrad is the powerful, the single, I think, most powerful stuff in Pytorch that allows you to do all this back propagation with just a single function, right? Yeah, anyone want to add something or any question?
Yeah, I think, how about now that we have these optimized values, can we set them as our initial parameters and see what the loss will be? Because I think we set the parameters as 0 and 1, but here we have 5.36 and minus 17. So for just experimenting sake, can we set them as initial parameters and see?
So that's here we are not in the next chapter. We'll train a neural network where we can do that iteration. So here we are building the mechanics, how it does, like what is happening. So in the next chapter, that is what we will see, where we will train this one iteratively. We take this to optimize weights to train the network. Remember here, we are not training neural network, right? We are using a toy problem, a linear problem. It's not even neural network. We are not using neural network here. We are just using, remember, optimize a toy problem, which is basically using, just trying to make the stuff easy to understand. The next chapter, that is what we see. Yeah. So is what Idris is asking is that now here we have our optimized weight, right? Can we use this optimized weights to go back and train this? So we can even put them here. For example, where the weight here, we can even put the weight here, right? You can even try that. It's very simple. Just copy these values here, right? And put them and make the prediction. So we can do that, to happen. But just trying to.
Hello, Shamsu, can I add some? Can I?
Yeah, add Hajia.
No, sorry, not add, ask.
Okay.
Even though you say we are dealing with a toy network, I'm just wondering, is this engine, AutoGrad engine, capable of dealing with a large architecture?
AutoGrad is capable of dealing. I think even these transformers, we use this. We use this Pytorch to do that, right? So AutoGrad, like one and so I don't know, like T-pipe, Amber. So you can use this Pytorch AutoGrad to do this kind of calculation. Yeah. So Idris, is it what you are saying? Because I can put it here. I don't know. Idris, is it what you are saying? We just put this weight of updated weight here. Is it what you mean? What you mean?
Yes. And what I want to see, Kaga, it happened that it's already optimized. So most of the losses, Kaga, so that's what I want to see.
Yeah. Yeah. So you can see here now we change the weight, optimized weights. You can see them here and this guy, and you can see this. Look at the loss. Can you see that? Can you see the loss from the? Can you see the loss? Can you see that? So this is optimized, the optimal. Yeah. So Hajia, I think to answer your question, this AutoGrad, Pytorch, this is the thing that now used in the real world in research, but there are open other frameworks like TensorFlow. But Pytorch is used to train even transformers, which are actually they call it post-deep learning. Post-deep learning transformers, because if you want to do like NLP and stuff like that, now those guys are the So any question or somebody want to add something? Tunde, Idris, Saada, Saeed, Palalu, Awal, Aliu, question or want to add something before we go to the next step? So the thing is, we still have a problem. What is the problem? So far, we have been manually updating the parameters using the computed gradient, and that may be fine for few parameters, right? We have been updating the parameters. What do we mean by this? Look at what we are doing. We update the parameters manually. This is manual. One minus one times. This is manual. Why can't we call a function? Oh no, this guy. Why don't we call a function backward, something like this, to do this automatically? One is manual way. Manual. What we need is an automatic way that dinga calculating changing parameters updating weight like this one, like this where we have Pytorch has backward that calculate everything. So we need to find a better way. This is still not optimized way to do that. So that is a problem. So it's still a problem because you can see in our previous where we use the manual approach, Najia, can you see we are using, remember this is Najia, right? The previous approach. We are using params minus learning rate times this, and we are still using it here. So we have a way to update this problem. So far, we have been manually updating the parameters using the computed gradient, and that is maybe fine for few parameters. But in real world use case, we have a lot of parameters. We can't even try to optimize algorithm to that. Now, for example, OpenAI was trained on 175 billion parameters. If you have been hearing what is called GPT-3 transformers, it has been trained on 175 billion parameters. So you can look at it here, how many parameters I have. We have only W and B, only single parameters. So this is fine to just show in a toy problem, but you need a best way to optimize way to actually change this parameter because in real world scenario, you have large number of parameters. So that is a problem that we need to address. For us to address this problem, Pytorch again comes to serve us with what we call optimizers, and this is the next stage for that. Pytorch come built in with what we call optimizers, right? So yeah, so the next thing we'll see is how Pytorch comes to save us from doing that manual stuff to automate this updating optimizers. So here they call optimizers in the session la carte. Wannan turancin ban san me ake nufi ba. Da akwai wanda zai fassara mana. Okay, let's go.
A la carte.
A la carte. Turancin ake nufi.
What I know is in Malay, if you go to buy
side dishes, what side dishes?
Yes, yeah. If you want only the main dish, you say a la carte. If you want
something,
the whole package, you say combo.
Yeah, French kalma ne ji abinda baya cikin package haka.
Yeah, you want it alone.
Yeah. So what they are saying, optimizers are a la carte kenan yanzu. Ba sa cikin dupla nan kenan. I don't know. So let's look at it. What the problem? So Pytorch abstract optimization, right? So this is what we mean. Pytorch now abstract optimization. Pytorch abstract optimization studied a way of users these tables having update each and every parameter. So what Pytorch does, because it builds stuff in a modular way. What we mean by a modular way is that it builds stuff in module that everything you want to do is in particular module, right? So if you look at it here, in the previous way, in the previous scenario here where we see AutoGrad, AutoGrad is basically implemented. We call just import Pytorch and AutoGrad is available. But when we use optimizers, it's implemented in a module called Torch and Optim. So for us to use optimizer, we call what we call Optim, import Torch Optim as Optim. And now here, this is the module Optim. And now here we can look at the optimizer. So look at the optimizers now. We have ADA, Delta, ADA, Grad, Adam, LG, optimizer, RMS from SGD. What we saw previously in the previous session is just the vanilla SGD gradient descent, right? So gradient descent, it has many versions, right? We have SGD with momentum, we have whatsoever. So, but what we saw is vanilla gradient descent. So we have different kind of optimizers. So it means if you are doing deep learning, even function or way to optimize those kind of your weight, there are different approach, different method, which they have their own advantages and disadvantages, which is not, I think, discussed in this session, but I think in the next session they have been discussed. So yeah, so let's look at how we can use optimizers. So optimizer, each optimizer actually exposes two methods, right? It exposes a method called zero grad, and it exposes a step. So a step method actually update your parameters, and zero grad set your parameters to zero. Remember here, we will see that. So let's look at it. So here, let me look at this Adam, one of them. So you can see we have Adam optimizer here, right? We have Adam. So I want to see what is inside this Adam optimizer, because we said each optimizer exposes two methods. zero grad and step. So here I want to see the Adam optimizer, but I don't want to look. I don't want to see this built-in hide this stuff. So I just put this function. I just remove this the first one and just give it. So you can see we have this method step and zero grad, and this step, when we call it, it will just update the parameters. Let's look at the magic. What happens? So let's look at the magic that optimizer can do for us. Remember here we create our values and we get them with tensor and we initialize and we change this one using the normalize it. So here we normalize it, right? So here you can see I'm using Copilot, GitHub Copilot is suggesting whatsoever I want to write. So for example, look at it here. Okay, let me show us something. This is something in deep learning as well. It can write code for you. Let's look at an example. So here I did something now. I define my values. Now I create my model, did something, and now I create my loss function. Remember? Now let's see how we can use gradient descent optimizers. So here we import our what do you call it? Optimizer, and now here we initialize our parameters, right? Params. Can you see that? We say 1, 0, and we set grad equals to, and we initiate our learning rate, right? Learning rate may be 1:5, right? Now, for us to use optimizers, we need to create an object. So let me show you something. Remember here, in the how can we update our weight? So for us to update our weight, what we basically do is this. This is very important. What we do for us to update our parameter, we say parameter minus learning rate times grade, right? Parameter times learning rate. So it means when we want to update our parameter, it has some parameters. It needs parameter, it needs learning rate, it needs grade. So here you can see, for you to create optimizer, which optimizer weight, we import the optimizer here. We're trying to create a construct optimizer object.
I think, Doctor, I think, Amina, can you mute your mic?
Yeah, so am I okay now? Is that okay now? Is that okay now?
Yes, sir.
Okay.
Yes, you can go on.
Yo, Nini kuma kai?
It's already mute. It's not Abdul Mumin, it's not me. My own is
Okay, sorry.
Okay, right. So here you can see, for us to optimize our weight, what we do basically is this. Oh no. What we use basically is this. We said, okay, parameters minus learning rate times gradient, right? This is how we optimize the weight, right? The parameters. So this means that if we want to create optimizer, that optimizer must have this learning rate and grad and whatsoever. So this is it. So for us to construct an object optimizer, here we said optim SGD. So we want to use SGD optimizer, gradient descent. Now we provide the parameters, we provide the learning rate. So you can see it takes some input, as I showed here. For us to create optimize, we need the parameters, the learning rate, and gradient, right? But here you can see we don't provide any gradient because the gradient will be calculated automatically using the backward probe, right? So this is how you create. So for any optimizer, you need to create or construct the object, right? So here you can see, I think this guy. So here you can see when I said no. Okay, so here let's create our optimizer. So here you can see you can use any optimizer, not SGD, but this is vanilla SGD you are using. So let's look at how we can use forward pass. Now, remember, for us to use forward pass, what we need to do is to create a model, create the loss, then you do backward propagation, right? Now, how can we optimize our weight? The way we do it, this is how we do optimize the weight, this minus it. But now with optimizers, function optimizer that we construct the object here and you call step on it. Optimizing them, they changing them parameters now. So this is what we said here previously. Remember that the optimizer method was two functions, zero grad and step. What step does update the value of those parameters according to the optimization strategy implemented? So here, what is mean that we update, we construct optimizer based on SGG, right? Based on SGG. Now, when we say optimizer, the step, it will update those parameters based on optimizer SGG. Now here, the parameters here. When we create them, then here we have some kind of parameters. So let's look at how we can put this in neural network. But you should know that if you want to, if you need to move a model to GPU. So remember, sometimes we move a model to GPU. Please do so before constructing optimizer. So before you construct the optimizer and then move your model and then to GPU. Okay, moving into to GPU, then you construct optimizer. Okay, I think don't construct optimizer, then you move the model after, because the optimizer would be different, the one on CPU and GPU. That's what they are saying. So what will be different of them with those on before the YA, something like that. So let's look at how we can do that. Put everything now together. We create a parameters here, and we create our line rate. We create our optimizer. So you can see we have a line rate, we have parameter, we have a parameter optimizer. Now this is the model. We create a model prediction. We make a loss. Now the next after doing loss is to optimize our. Okay, so this one I will come to it. So let me remove it first. Now let me explain this. So when we create our loss, what do? We need to do what? Backward propagation, right? We need to do backward. When we do backward propagation, then we need to do what? Do optimize, call step to optimize the parameters as we do here. I always like to give this comparison that we do back propagate. Can you see prediction, loss, back propagation using gradient? Shine muka yi yanzu amfani da backward here, and parameter update. Now we are using the step optimizer. So you can see everything is becoming more simpler with Pytorch, right? So it is easy to do that. But here I remove something. Remember, as I said, we zero grad. So if we go for iteration, zero the gradient buffer of all optimized variable, the previous one. So it will not be accumulating the parameter gradient, as I said previously. So let's look at how we can put this in a training loop. Number of epoch, optimizer, parameters, given these guys, and right. And you can see this is the training model. This is a loss, zero grad. Loss, backward optimization step, and this zero grad. Remember, this is what we do here. Let me show us here. We do it here. Remember here. Yep. Remember here. I use this guy. If param grad is not zero, param set it to zero, right? So this is what I'm doing here again. So here, a better way is just to use this. Can you see that? Optimizer, because we are doing the optimizer, create optimizer now. We say optimizer the grad, zero grad to, because here in the previous one you can see we are calling params.grad, right? So this depends on gradient parameter. The grad, it depends on gradient, but now we already have optimizer, so we can do that. So this is actually what's happening, and now this is our training loop. So the training loop is getting smaller and even looking better. But here you can see we know all this. We don't need to. This is Python, right? If epoch modulo 500 is equals to 0. What? So this is Python. Who can tell us what this is doing? I don't need to explain this. What is this? I assume
at every 500 epochs,
yeah,
like,
yeah,
it should print that particular statement there.
Yep.
So after from 0, it will print. It will print at 500. Then it will print again at 1000 epoch. Then it will print at 1500. It will keep printing after each 500 epoch.
Yep. So that's what we mean. So here, this is what we have. So let's do the training. So create our parameters here. We create our line rate. We create our parameter optimizer. We're using SGD. And now training loop. This is a function. What you should know is that this function, so they actually defining the issue. So this kind of structure, for all you are learning, this is the structure. So here we put the parameter, we set the initial parameters, and now we call the function training loop, number of epoch, optimizer, we give the optimizer, number of epoch parameters, which are this, TU and T, these are the input and the true value, and now we calculate this stuff, right? So you can see this, can you see that our optimized weights, they are still the same thing as the previous two? They are still the same with this guy. Can you see it's still the same with this guy? With this guy, it is still the same with this guy as well that we do, right? It's still the same with this guy. Can you see that? But now we are using beta, we're using optimizer, right? So again, we get the same result as before. Great. This further confirmed that we know how to descend a gradient by hand. Yeah. So anyone want to add something or any question before we move to the next? Anyone want to add something? Or question? Okay, so let's move on if there's no question. So, but we use gradient descent here, right? SGD, which is stochastic gradient descent. But gradient descent has some challenges. The vanilla mini batch gradient descent does not guarantee convergence. So sometimes we have, it does not guarantee convergence to base parameters. It has some kind of problem. One of them is choosing a proper learning rate can be difficult. So here, what is the problem is that maybe you have a learning rate here, right? So if this thing, it does not work well, you need to come back and select a beta learning rate. So you need to choose a particular learning rate. You don't know which learning rate can be optimized. So this is a bit challenging. Choosing a proper learning rate can be difficult. A learning rate that is too small leads to painfully slow convergence. So let's look at this is a learning rate. When you have a learning rate very small, it will go slow, painfully. As though you have billions parameters, this learning too slow convergence because this is a minimum. We always want to go to the minimum. But also when you give a very large learning rate, it will do like this. How my is what you converging a local minimum? My G1 wajen itaewon iskanci. You see that? So what we need is we need a just right, a just good learning rate. Now it can move. Yes, move. Can you see that? Optimal learning rate it reaches. So this is very difficult to choose what is the best learning rate. You can see that while learning rate that is too large can hinder convergence and cause the loss function to fluctuate around the minimum or even diverge. You can see the loss function now can diverge here. It said this is your minimum. Can you see I diverging Bemazo number? So this is a bit difficult. Learning rate scheduler. So sometimes you can set what we call learning rate scheduler. They try to adjust the learning rate during the training. So what you should have is you can have a learning rate scheduler that change the learning rate, but that is also there is a problem. This schedule and threshold, however, have to be defined in advance, and that's able to adapt it. So you need to define these learning rate schedulers, but since you need to define them, they will not adapt to data set. Your data, if you have new data set, you need to change the scheduler. So they will not adapt. So we need a better way that will a learning rate that will adapt to the data set. There's also another challenge that the same learning rate applies to the all parameters. So for example, we have two parameters, right? Maybe we have the weight and bias. So using this approach, this learning will apply to all gradients. So if one gradient is large and another one is small, as I explained yesterday, the problem. Another key problem is also non-convex. Another key challenge of minimizing highly non-convex error function for neural network is avoid converging getting trapped. So we have what is called non-convex. So these problems are convex. That is, you have a single minima. This is a minimum, only minimum. One and none minima. Minima maybe no. This is called functions, right? A convex function is the one that has a single minima. What do I mean? A line here. I draw a line here. Can you see I draw a line here? Then when I draw a line here, everything point will be and below the line. If I draw a line here, everything. But a non-convex problem, like now when I draw a line here, you can see there are many stuff like that. So where we have this is non-convex, we have global minima, we have another minima. So in SGD, stochastic gradient descent, you may come here and you are a local minima, and you may find it difficult to come out from local minima to come and reach the global minima. Yes.
What you are sharing, I don't think I'm seeing what you are sharing. Is it my network or is it that you are not sharing the right screen?
Okay, what are you saying? What am I sharing?
Yeah, I think, is this global minima, local minima diagram that you're sharing now?
Yes, that's what it's sharing.
Okay, I think it's my network, is a delay, sorry.
Okay, what I'm sharing is the problem of stochastic gradient descent, right? One of them is like, there are many that I mentioned here. Difficult to choose a proper learning rate. Using learning rate scheduler, which you need to define first, and it will not adapt to your data set. And the same learning rate is applied to both weight and bias. And now it is difficult to also, if you have, because neural networks, their function is non-convex. Right, so this is non-convex function. They may have a local minima and they have global minima. So you may be stuck at local minima, and now assume you may not go to global. So this is one of the problems of this. And now the solution is to do better ways to do another kind of gradient based optimization method, which we see certainly. Also, there is what we call stochastic gradient with momentum. The book did not discuss it, but just trying to introduce it to show us, maybe we can read it along the way we see it. So you can have here, you can see here where we are using stochastic gradient descent. We said SGD, right? We give a land rate. Sometimes you may see some people, they would say, okay, momentum. So we'll give, can you see land rate, momentum? Can you see momentum? So one good thing like with this is like you can see SGD. Now SGD, what are some of the parameters in the SGD? Learner rate, which is float momentum. Can you see that? And you can see here we are trying to explain the moment. Yeah, can you see momentum is equal to 0.9? So what we mean here is that we can set our momentum here to some value. So what is the meaning of momentum? So momentum is basically, this is, let me just, I like to explain with graph, with pictures. So let's assume this is a point and you are trying to move to go to the solution, your minima. This is a normal without momentum. It will go doing like this manner, going like this without minimum, right? But if you set momentum, it will move faster to the solution. So with momentum, if you are, can you see that? It will move faster like this. So this is what we mean stochastic gradient with momentum, and you can set your momentum with that. And yeah, so this is some theory behind that, and I think we'll see just into the right. So that is some of the issue with stochastic gradient and some of the stochastic gradient with momentum. And let's now look at the doing the optimization with other optimizers. Anyone want to add something or any question? Yes, ask question or question. I'll add something. Falalu, you want to add something or question something?
Please,
no,
why
doctor.
can't you just, okay.
Yes, Hajia.
And this particular if epoch.
Yes, Hajia.
100. Can you, in Tunde has explained it, but I didn't get it very well. That particular question you asked. About
Hajia.
Yeah, I heard that.
Tunde, you want to add something?
Yes, I heard that question. So she was trying to ask concerning that line of code,
okay,
where it was printing the loss at every epoch. So it's actually a mathematical representation, mathematical function. Ow.
The
problem is from you.
Okay, so energy now.
Yes, the problem is from me. Yeah, I can see my network. Yes, I'm on stop. Yo, energy. Yeah, I can hear you today.
Okay, so let me continue. Okay, I said that line of code was trying to print the loss at every 500 epochs. So epoch divided by 500 will give us a particular value. And if it's divisible by 500 and there will be no remainder, that means at that point it should print it. Take for instance, if you pick 0 divided by 500, the modulus is 0, so it's not going to print at that point. Then when it gets to 500, it will do 500 divided by 500. It's 1, no remainder. So at that point, it will print.
Yeah.
Then if you
modular
go to
operation.
Yes, so that's what it's doing at every point. So if you pick 1,500 divided by 500, you get a value. There's no remainder. At that point, it will also print the loss. So that's what that line is doing.
So let me say it what Tunde is saying. So I didn't say this. So what this we all know modular operation, right? Given this, if I have 1,000, modulo 500, this would be 0, right? If I have 1,005 modulo 500, will give you 0. We know modular operation, right? So what this is saying, we are not printing the epoch in each. We are not printing the loss in each case. Here we are just printing the epoch in where the modulo of 500 is 0. So you can see 500. Can you see that? So this is just a modular operation. Yeah. So yeah, want to add something today or anyone again?
Probably the reason why it is they're printing at every 500 epoch is so as not to bombard your screen with plenty lines when they are reporting the epoch. So you just want to compartmentalize it and just check your loss at some certain steps.
Yeah. So what this guy is saying, what Tunde is saying, like you can see here, we can have some loss that we can see in our screen, right? So let me change it to 1,000. So let's look at what will happen. Can you see my loss? I just see some stuff, right? Something that I can see my screen. But if so this is just way to optimize what we can see in the screen. So this is nothing, it does not concern about our training the model, just trying for us to see what we can see in the eye, to see the performance. Yeah. Okay, good.
I have a question. Hello?
Yes, we can hear you.
So sorry, most of what you are explaining, Doctor, is I don't see them on my screen. So maybe it takes quite a while before I see what you are explaining. So I don't know, is it only me or is it we are many here that encounter this problem?
Can you see my screen?
From my side, I think the network is a bit slow.
Yes, we can see the
Can you see my screen?
Maybe when you are scrolling down, you are explaining something else while the screen is still showing something else. So I don't know whether it's only me or we are many. If it's only me, I'll change my network.
Okay, it is. I'm having the same problem.
Yeah, I think I'm having is delaying.
Yeah, it is delaying.
Okay. So I think the issue is not with you guys today. I think I'm not sure why my network is giving me that kind of issue. I think maybe with my network, because I can see one time my network show did the network in now, but then Nigeria Amade is still doing like Nigerian network. But bear with me today. Yeah, we want to finish. Let's go. So testing other optimizers. So we saw the gradient descent has. Can you hear me now? All? Can you hear me?
Yeah, I can hear you.
We have no problem hearing what you're saying, but most of the times is the screen when you're trying to change certain things that delays a little.
Okay, so let's go to the so we have seen now that the gradient descent has some issue, right? The gradient descent has an issue. So the best way we want to do is we need to use what we call adaptive optimizers. Adaptive. What do we mean by adaptive? From the name, they adapt your data and your data set, and they even adapt if you have weight and bias. If the gradient of weight is large, it will use a different learning rate for the weight. If the gradient of bias is small, it will use a different learning rate for the small. That is what we call adaptive learning optimizers. So we have many adaptive learning. They adaptively set the learning rate according to a parameter. So because we have many parameters that have higher gradient or frequent update should have slower learning rate. So if the parameter has slower learning rate, parameters that have low gradient or frequent update, infrequent update should have faster learning rate. So so we can see here that we have adaptive optimizers. So adaptive optimizers include Adam. So Adam, one of them. is basically adaptive optimizers. So for us to do that, what we need to do is just to create optimizer object. So for us to use adaptive Adam optimizer, it's something we saw. It's some create your parameter. Here you can see we set our ladder rate to be 1:1, right? And we set our optim.adam. It means we are using adaptive optimizer. We put the parameter, we put our ladder rate. Can you see that? And now number of effort is 2,000, right? And now here you can see we are using we are back to original TU, not normalized. Here you can see it's not normal in TUN. It's not normal. We are using TU. That is what they want to explain here. So here using Adam. Let's run see what will happen now. We are using Adam. So since we are using Adam here, okay. Anyway, I changed this guy to So you can see while we are using the Adams, it still gives us 0.573 and minus 1.73. It's the same weights optimized what we saw previously. Can you see them? The sum of my weight. But what happened here? You can see that we have not actually used the normalized input, and also here we use a small learning rate -1. So there is some issue. There is some thing with Adam. It is a lot less sensitive to the scaling of the parameters. So you don't need to scale your parameters in Adam. You can see we have not sent. So it's sensitive that we can go using the original non-parameterized input, non-normalized input. So Adam is actually less sensitive to your input. You can just go. You can see that we can increase the learning rate. Also, we increase the learning rate to 1:1 -1:1, not 1:2 or 4. That can and the Adam won't even blink. It gives us the sample. So this you can see one of the advantage of one of the optimizers, which is Adam. So that is about optimizers. Then the last part of the book, the chapter they discuss about training, validation, and overfitting. Training, validation, or overfitting. We all know this training. When you have your data, you set for training and you set for validation set, and now you do parameter training, optimization, whatsoever. You choose everything here, you tune your parameter, and now finally you can use a validation set with the tuning model to train model to actually use validation set. That is the last part that you have not to use for training to see the performance. So this is what they discuss about, but there is an issue related to this training validation, and that we have what we call overfitting. So this they discuss about the notion of overfitting, but let's look at what they do. So as you can see here, we have two different kind of loss. We have what we call training loss. So what we are saying here is the loss on training, right? We are calculating the loss of training. But now we say we're going to divide our data set, training set and validation set. Remember, the reason why is that when we want to do training, we don't want to train our model in our old data. We need to take some part. That is what we show in Kepler's theory. Kepler's also in our basic machine learning, that is what we do. So in Kepler's, that's what he do. He takes given the complete data, get a lot of data, choose split the data so that we can work on part on it and keep independent for validation. He takes some part to train the model and keep the part of validation. Now, finally, after Kagama training on Komai, they validate the model on the independent observation. So this is what they are trying to tell us, that we need to take some independent where we can train, we can test so that if you are training your optimizers here, you are you are playing with the model to find the best optimizer. So the model has seen all this data set and he memorized it. He will not give you an optimal performance to say yes, my model, because you memorize it. So you need to test this model account data set in the beginning model, and that is validation set. So this is what they are trying to do. But now we now have two kind of error that is on training set, and error that we'll get when we use validation set. Now, how can we compare them? That is now what this section is. How can you compare the error on training set, and how can you compare the error on validation set? So this is it, evaluating the training loss. So it means we have training loss. The training loss will tell us if our model can fit the training set at all. In other words, if our model has enough capacity to process the relevant information. So if your data has a relationship, That is, for example, you have your data set. You said this to it. This is good, it's positive. This is good, it's positive. This is excellent, it's positive. This is bad, negative. This is bad, this is what, negative. You can see you have a relationship that the model can learn. If there is a relationship in your data set, then the training loss, you will get a training loss that is decreasing. That if the training loss is not decreasing, chances that the model is too simple of the data, is too simple for the data. Two things. When you are training on the training set, if the model is not decreasing, then the model you are using is too simple. It's not complex model. Maybe you are using linear regression, then change it to use maybe a complex model, right? It's something that is more complex. Maybe you can use in machine learning. You can use maybe what we call maybe gradient boosting on some stuff like that. But the idea is this: in data, if there is a relationship in your data set that is they are related, then your training loss when you start training will be higher at the beginning, but it must reduce. But idan baya raguwa, then there is problem at your training. So that's what they are saying. Rule 1: if the training loss is not decreasing, chances are the model is too simple for the data. Another possibility is that our data just don't contain meaningful information that led it to explain the output. So for example, now you have your training data. For example, I have a tweet, this is good. And when I say this is good, I put the output to be white, right? Or whatsoever. If there is no relationship between them, so it means the model cannot learn. But if there is a relationship, then that is. So these are the two scenarios that if your training loss must decrease. One, which we discussed yesterday, is that the model is too simple. That is, the model to fit the data is very simple model, but we need to use a very complex model. How can we make some complex model? There is some kind of parameters that you can use in machine learning to make your model more complex, and we see them. But also there is, so here we said evaluation training loss here, right? Then we have what is called generalization loss. Because if we now test our model, we use our model to train, to use validation set, then we are trying to find whether the model will actually generalize on unseen data set. Now, this is in rule 2. If the training loss and the validation loss diverge, that is, the validation set does not decrease along with the training set, we are overfitting. So the idea is this: when you are training, the training loss must be reducing, and the validation set reducing. They must be reducing at the same time. In the side reducing, maybe training set is reducing, and my validation set is increasing to we are overfitting, meaning that our model learn is too complex that it memorizes everything at training loss, that it can map any input to its output, but it cannot learn on the test set, on the validation set. So these are two issues that we can discuss. So there are several ways actually to achieve this, making a model. What we can use penalization terms, right, in machine learning, and we can add noise. We can use simpler model. If we are overfitting, we can use penalization, where we can use L1 or L2 in machine learning, so that we can make our model less complex, or we can add samples, or we can use a simple model. So meaning that if you are overfitting, then your model is too complex, then you just a simpler model. But let's look at the practical way on how we can actually note something is overfitting or not overfitting. Let's look at example. So anyone want to add something before we go to the real scenario, how we can identify overfitting? Anyone want to add something? No question? Right. We have a few minutes. Let me quickly go. So this is our data set. What they are trying to do is now to divide our data set from training set to validation set. But here they are using, if you remember in scikit-learn, we can use our function called, we can use our function that actually divide our data set into training or validation whatsoever. But here they want to use, Pytorch to do that division, but it doesn't matter. So what we are trying to do here is just take some sample of our data set to be training and take some sample to be the validation set. So here we take the sample of the data set. So the shape, it gives us how many sample do we have? We have 11 sample, right? 1, 2, 3, up to 11. So we have 11 samples. So it means we can take some part to be training. So here I said, okay, number of validation is, I said 0.2 times number of sample. That is, I'm taking 2% of the data of the sample. 2% of the sample, I will take the 2% to be my training set. Yeah, so here you can see I said shuffle the index. So here they use what we call random.pam. That is the randomly shuffle the index of the number of the samples. So you can see this is the sample. Here we have they randomly shuffle the index, which is 0. The first one before is 1, but they shuffle them. So we have shuffle.
20%.
Yeah, it's to, so we can use now shuffle index. Now we can use from the beginning to the minus n val. N val is this guy, which is 2, right? So remember, if you are indexing in whether in Python, in NumPy or Pandas, so from -2, it means it starts from the beginning, it's from the last, which is what? The training, it stopped from the beginning to the last, which will be like, it will start from the beginning to the last 2, it will not read the last 2, but the validation will start from the last 2 and to the end, which is 2. So this is basically our Python experience. I believe you all know how to do this. Basically just they are dividing the data. If you don't know this, I urge you can revisit the indexing stuff. And yeah, so when we see basically what we try to do now in those steps is just try to take Guda Takwas to be training set and Guda View to be validation set. That is what we did. And that is normal Python. It's nothing concerned with the Pytorch whatsoever, but we just use Pytorch random pump because sometimes if we want to take some samples, we take that, we randomize them first before we take them. That is the notion machine learning. So here we will train our data set on this sample, and now we validate performance in this validation set. So if you don't understand it, don't be confused. You can do them with scikit-learn, how you can divide your data set. So that's what we do. Now let's see what we can do. Now we can take our data set now and now take the validation train, normalize and validation. So each one we have the validation and we have the train. So what they are trying to do here, we will try to do the training of our machine learning using their stuff, using the validation and also using the train. So the point I want to say here is this. You can see here in the previous example, we are just training it, we are just having the loss on training, right? On training set, loss on training. But we need to see the loss also on validation set. Now we understand that we need to divide our data set into validation set. Now we will implement that thing in our training loop. So let's look at our training loop now. Look at our training loop. The same thing we use without validation set. Oh, this is with validation set, right? Model with validation set. Okay, this is the model without validation set, right? With just loss that we have. But now here we have training set. So you can see here I'm training on training data. I'm finding the loss on the training loss. And now here I have validation. Can you see that? Train on the validation, the model, and now on the validation loss. Now you can see I call my optimizer, the grad, and now I call my back propagate on training loss. Can you see that on training loss? And now I said optimizer the step that is to update those parameters, right? And now here I'm just printing some epoch. Let's look at what will happen. Okay, now I modify. This is a modified version of our algorithm. The only difference is that we now put this guy. That is validation loss, validation. So we now do validation instead of training only. So we also train on validation part. So that is the only issue. So now let's train our model. The something number of parameters, learning rate, optimizers, we define them. Then we have epoch parameters. We provide the training set, the validation set on training, and the training set on the other part and the validation. And now we train this. I believe when we have the background of machine learning, we know what we mean by validation, all those. So you can see now here you have training loss. Can you see that? Because you can see here we have epoch training loss. We have the epoch, and you know all this one, right? Printing in Pytorch, in Python. We have we assume that everyone here is having the Python understanding. That is why some stuff we may not explain it vividly, but this is basic. We should know those. So here is what we call F string, where we do printing in Python. If you want to print something that involve the string and also values, we use this F only. And now here, when we want to print our epoch, we put them in this format. So this will print that. And now this is the validation loss. That is why here you can see we have training loss, we have validation loss, right? Loss. So if you are not very compatible with Python, you can start joining us our machine learning class we use every Saturday and Sunday. We are learning Python and those stuff. So if you are not confident on Python, you can. So you can see here we have now training loss and validation loss. Now we have this. So we can see what is happening now. What is happening is the training loss decreasing. Training loss 92, 26, 19, 95 is decreasing. What about the validation loss? 23, 59, 73, 29, 10, 4, 2. So we have some kind of irregular pattern here. It just start with it, 79, but yeah. So because our data point is very small, it may not perfectly work well as we expected. But in a general sense, we can see that training is going low, and also validation is what going low. So you can see we note that the validation loss is higher than our training loss, right? Although not by order of magnitude. We expect a model to perform better on the training set since the model. So we can see that the model, even though here we can see the validation loss is 3, but this is not the same scenario. I can see from the book that is what they have. If you look at it, we may not have the same figure, the training loss. So always, which one should be always lower? Always the training loss will be smaller than the validation loss, because we train the model on it and it's in the data, but this is not the case, I guess, because of the problem of some stochastic problem. But I think in the book, you can see that this is lower than this one. So the issue of overfitting is this. We have 4 issues that we can talk about. Oh, we have 5 minutes. Just forgive me. I have to explain these guys. So we can have the issue about overfitting 4 scenarios. So let's assume that this is loss and this is iteration. And let's assume that we are going to discuss about possible issues of when you do your plotting to find out you are overfitting or not. So we are looking at training and validation loss. So the training loss is this solid line. This dot dot is validation loss. Now, what happens if you are validation loss and training loss? Gaba ɗaya anan ba sa decreasing. Can you see that? Ba sa saukowa. Misali nan suna 70. Amma ba su ragu ba, kawai suna kan 70 din suke ta tafiya 70. So in this case, training and validation loss do not decrease. The model is not learning due to no information in the data and insufficient capacity of the model. So idan kana da irin wannan, you plot your training loss and the model din ba abin da yake ganewa, whether the model is so simple but they are learning the different data, ko kuma model din there is no relationship of your data set. So whenever we plot our loss on the validation and training loss, we see this kind of structure, model by learning. The next is training loss decrease while validation loss increase. What about this? Training loss, can you see the training loss yana decreasing, right? Yana 70, for example, yana decreasing 50, but validation loss may yana increase. So in this case, training loss decrease while validation loss, we are clearly doing what is called overfitting. Meaning the loss is actually reducing on training loss. It means that the model is learning very well on the data. It's learning very well on the data. The model maybe is too complex or whatever, but it's not learning anything on the validation set. So you are overfitting. What you need to do to reduce overfitting is maybe to add some penalizer model or some to do that. But this is what we call overfitting. Another issue is training and validation loss decrease exactly in tandem. Performance may be improved further as the model is not at that. So when we have the training loss, can you see that? And they are decreasing in tandem. Wannan shi muke so. This is a perfect scenario. The training loss and validation, they are decreasing in tandem. So it means that they are the way the training is learning, also the model is also in performance, having the same performance. But you can even trend further. Training and validations have different absolute value, but similar trend. Overfitting is under control. So here, the model is, they said the training and validation have different absolute values. So they have the same value decreasing. So here you are not actually underfitting, but we can say overfitting is undercrow. You will not overfit, but you can improve the performance. So this is one of the issues we can understand about overfitting and underfitting. You can see that when you are doing training in deep learning, the main goal is to see both training loss and validation loss decreasing. While ideally both loss will be roughly the same value, as long as the validation loss stays reasonably close to the training loss, we know that our model is continuously generalizing out there. So what we know that if these values they are very close, then we can say that our model is learning from our data. Finally, finally, what I want to talk is autograd need switching off. What we discover about this, we know that we only call backward probe on our training loss. Look at it. Here we have training loss, we have validation loss, but we call only our backward on training loss, right? We don't call backward on the validation loss. So you should know this thing, because we are doing back propagation on training loss, not validation loss. So here, we should know that we are not actually using that. So in that case, what we need to do is we need to, if we are using our validation loss, our parameters here, they have gradient is set to true, their gradient, and the model will also building graph for validation loss. At the backbone of the Pytorch, though we are not calling the backward on the training loss, but this thing will take a lot of time, will take our memory and speed, because it is parameter are set to be set to autograd is true. So we want to make calculating of training loss without parameter gradient is true. So we can use what we call here, we can put the calculation of the validation to be under what we call touch.nograd. So kamar yadda na faɗa ɗazu, therefore now calculation of the validation loss mun saka shi a cikin wani waje, in the sense that the grad the gradient is set to false. So this will say your gradient is set to false. Here is this, and now you do your validations loss here. But it's still the something the one. But abinda muke so anan shine muna son mu optimize in time ɗinmu, because parameters ɗinmu here they have been set to autograd to true, but muna so mu yi wannan calculation tunda ba ma going back calculating backward on it, muna son mu yi calculation din wannan with autograd set to false. So we can put that part inside what we call with touch.nograd, mean you turn off the autograd, temporary set of all local stuff. So yeah, so you can see here we have everything here, and yeah, this is something. So they say we won't see any meaningful advantage in terms of speed or memory consumption on our small program. However, for large model, the difference can add up. We can make sure this works by checking the value of the required grad attribute. So this is what we have today. The tomorrow chapter, basically, we're using, today what we see, we use a toy example where we go through how we can actually show what is called the mechanics of learning, right? How learning works. So tomorrow, we'll see how we can use neural network. Today, we didn't use neural network, right? But today we can see how we can use deep learning with the neural network. So I think for today, from the beginning today, we'll now build enough intuition how we can use Pytorch to start training deep learning neural network. From using the chapter of tensors, using the all other chapters, we now build enough intuition to start doing neural training neural. So tomorrow, not tomorrow.
Next week. Not tomorrow. Not tomorrow.
So we will use Wednesday, because we don't have enough time. We want to go. Remember, one of our objectives is to try to get enough intuition on Pytorch. Then we go and do the summer school course that we ask everyone to apply. That we will go through, that they will teach deep learning, because it's really summer school. So we want to get intuition on how we can use Pytorch. So now we will stop this book probably at chapter 10, meaning we get the good enough intuition, and now we'll go back to that summer school. We start learning deep learning from the beginning. So we start teaching from the beginning. So if you don't understand everything here, but you understand how we use Pytorch, they will even teach Pytorch in that summer school in the what we go, but we get a better intuition here. So because we don't have much time, and we want to start doing the stuff. On Wednesday, we're actually going to have our next session, chapter 6. Ibrahim will go through the.
Excuse me, doctor. Hello?
Yes, Ajia. Yes, Ajia.
Yeah, well, Dr. Allah, I'm suggesting if there is no problem, let it be Tuesday or Thursday.
Okay, let's it be Thursday, so we can use Thursday.
Yeah, on Wednesday I have appointment at KL for my passport.
Okay, so maybe we can discuss in the group. For now, we can put it in on Thursday. So Ibrahim will do the presentation of chapter 6 on Thursday, and chapter 7. Idris will do chapter 7 on Saturday, and I will do chapter 8 on Sunday. Week after, on Sunday or another day. But what I'm trying to say, we need to move fast to finish this Pytorch basic. Then we can start and go to start the deep learning from that course. Yeah. So any question or want to add something? Dr. Ibrahim.
Now, Doctor.
Yeah, well, that came in Thursday, so inshallah, yeah, if everyone is okay with Thursday, Dr. Idris Kuma on Saturday is chapter 7. Then after Idris Zanyimana chapter 8. Yeah. So I think from yes.
Can we finish the chapter 6 on the Thursday? Taking note of we needed 2 days to finish this one.
Yeah. So if Idamba Mugamaba, we can also still discuss. Kuma especially also I see.
I'll try to make it in 1 day.
Actually.
Okay, no problem.
Okay, I also see chapter like 8 is really large, and we see what we can do. And in one location in putting in Abu Dewa so that Amadi maybe in and I feel slow sometimes. So sorry for taking your time for 2 days going through one chapter.